Okay, we're going to talk a little bit about quadrilaterals. Now, what problems can we encounter if we simply define a quadrilateral ABCD as the union of line segments, segment AB, segment BC, segment CD, and segment DA? And what are any of these issues, did any of these issues come up when we studied triangles? And then how should we define a quadrilateral ABCD in order to avoid these issues? So, actually pause the video for a minute, think about this, and then come back and see if you can. I'll come up with 5 different things that we have to check for. Pause now. Okay, now that you're back, let's see. One thing you may have come up with is this. First of all, we have to make sure the points are distinct. If they're not distinct, then it could degenerate down to a single point or maybe a line segment or a triangle. And of course, this problem exists in defining triangles. If you remember, when we defined triangles, we had to make sure that the points were 3 distinct points. So we're going to make sure that A, B, C, D are distinct points in our definition of a quadrilateral. The other problem is that also showed up in triangles also is we have to make sure that each of the line segments A, B, B, C, C, D, and D, A are actually defined. So we know that any 2 non-antipodal points, there's exactly 1 line segment with those 2 things as endpoints. But if we have an antipodal pair in our group of 3 points for triangles or 4 points for quadrilaterals, then the triangle or quadrilateral doesn't exist. So we need to make sure that we have 4 distinct points and no 2 of them are antipodal. What else could we have? Well, let's look at our basic figure here. So here's a figure that we have, and here's just 4 points. So we notice that if we have, if we're not careful here, we could have, it could degenerate if we had a pair of, some of them were the same. We could just get a triangle, or a line segment, or a point. Okay. What other problems could we have here? Well, one of the problems we could have is if we did something like this, if we had some of them in a line, then we could get maybe just a line segment, or maybe something that looks like this, or even just this, which is a triangle. So that's another problem that we could have. So we could have, if these are all in a line, then we just get a line segment, even if they're all distinct. Or if 3 of them are in a line, the other one's not, then we get a triangle. Or or we might get this situation here, where we get a triangle and another segment sticking out. We don't want any of these things to be quadrilaterals. Okay? And then we also run into another problem right here. And this is the problem where we have the thing basically crosses over itself. And so this will say it's not simple. So if we were to trace this out, it traces over itself at some point, at this yellow point. So if we trace around to A to B to C to D to back to A, we cross a point twice. Of course, we cross A at the beginning and ending point twice, but that's okay. But in the middle we cross again, and that's not simple. We want to eliminate that possibility. That's not something we had to worry about with triangles, because given any 3 triangles, as long as they were not in a line and they were not an antipodal pair, you could trace around there and you'd never retrace it. But one thing that doesn't show up in any manipulations of these things here is that all 4 of these points are actually in the same plane. And that can be a problem. If they're not in the same plane, that can be a problem here. So think of this box as being 3-dimensional box here. We go along the front edge, the side edge, and then we go across these here, across the back diagonal and the diagonal on this side. And now we have something that's kind of like a quadrilateral. It's simple, it's closed. Okay, it's closed, so you go all the way around it, you end up where you started. But so it's simple and closed, but it's not all in a plane, and we don't want that to be a quadrilateral either. Now some people will define, have other things for these. They'll call maybe something like this thing right here a quadrangle, or maybe they'll allow something like this to be involved. And those are sort of generalizations of a quadrilateral. But our definition, we want to eliminate all these possibilities here. Now, when you're building a general quadrilateral in Sketchpad, it's really hard to build something like this to where you can't get it to degenerate. So, you know, if you make this point free to move, there is some point in here where they actually are in a straight line when you manipulate it, and of course that's no longer a quadrilateral, and it's real easy to get it to be non-simple here. So when you're doing this, I'm not going to worry too much about this because it's so hard, if not impossible, to eliminate these degenerate cases, or degenerate where this gets so short that eventually it becomes a point. Now you're back down to a triangle. So I'm not going to worry too much about these sort of degenerative things, but we'll just know that if we, there's probably ways to push it so that it degenerates a little bit. But then, of course, those things are not quadrilateral. So how can we define a quadrilateral? Well, we'll get to that down here. So one way to do it is this way right here. So let ABCD be a set of distinct coplanar points, no 3 of which are collinear, and no 2 of which are an antipodal pair. So we've eliminated some of those possibilities. And then we define the union of line segments AB, BC, CD, and DA as to be the quadrilateral ABCD, abbreviated quad ABCD, if and only if the only intersections of these 4 line segments are at the endpoints A, B, C, and D. And so that makes it simple. In this case, we define the points A, B, C, and D as the vertices of the triangle ABCD. Pairs of vertices, A and C, and then the B and D are called opposite vertices. Any pair of vertices endpoints to the side of the quadrilateral of which are endpoints of the same side, I should make that clear, of a quadrilateral are called consecutive vertices. So A and B are consecutive, D and A are consecutive, for example. The line segments, just as in triangles, AB, BC, CD, and DA, all those line segments are called the sides of the quadrilateral. Sides of quadrilateral which do not intersect are called opposite sides of the quadrilateral. Sides which do intersect are called consecutive sides. We will use consecutive, not adjacent here, for those, for the vertices and sides like that. And then if you connect up the other line segments, AC and BD, those are called the diagonals of the quadrilateral. Now that's the formal way we're going to define these, but there's another way to go at this. It's a little bit more general, but it's a little more complicated. Okay? And this requires we know a little bit of analysis here. So we say a function f mapping an interval I of the real numbers to the points in the geometry, we say that the function is continuous at x if and only if for every epsilon greater than 0 there exists a delta greater than 0, so that if y is a real number in I such that the absolute value of x minus y is less than delta, then the distance from f of x to f of y is less than epsilon. So remember, f of x and f of y are points, and we're talking about the distance in the distance metric for the geometry there. And here x and y are real numbers, so we're talking about the function absolute value of x minus y there. So if x and y are close to each other, within delta of each other, then f of x and f of y are close to each other in terms of their distance being less than epsilon. So this should be fairly familiar to you from your calculus classes. Now, a function mapping an interval I of the real numbers to the points in the geometry is a continuous function if and only if it's continuous at every x, for every x in that interval. So a continuous curve is a geometric figure which is the range of a continuous function from some interval of the real numbers to points in the geometry. So intuitively what this means is we can take a continuous curve and we can draw it without picking up our pencil. that's a continuous curve. No breaks in it. A polygonal curve is a continuous curve that is made up strictly of line segments. Now, these curves could be maybe in multi-dimensions, like in 3 dimensions. Okay, but if we restrict it to a plane, then we have plane curve. So a plane curve is a continuous curve consisting of a set of coplanar points. So what I have drawn here are plane curves. A closed curve is a continuous curve that begins and ends at the same place. Okay, so that one's a closed curve. Okay, so formally we say a closed curve is a continuous curve such that the image of a closed interval from a to b of the real numbers under a continuous function f, and f of a and f of b are the same thing. So intuitively that just means it begins and ends at the same place. Okay. Now, a curve is a simple curve if it's the image of a continuous function, okay, but it doesn't cross itself. So that would be a simple curve. For example, these two curves here, well, all 3 of these curves here are not simple because they cross over themselves. This one right there at that point, this one several times, this one at a point right there. So formally, a curve is simple if and only it's the image of a continuous function f from an interval I of the real numbers to the geometry, or points in the geometry, so that f of x equals f of y if and only if x equals y, or x and y are endpoints of the interval. So the only place it could repeat itself is at the ends. So a simple closed plane curve, okay, is called a closed plane figure, and it begins and ends at the same point, but otherwise doesn't repeat anywhere. So that's a closed plane figure. So a region of a plane is connected if and only if given any 2 points in the region there exists a continuous plane curve contained entirely in the region that begins at one point and ends at the other point. So, for example, anywhere I am inside this figure here, it's connected because I can make a continuous curve from one to the other. Okay, but these 2 regions are not connected because I can't go from this region to this region without going through at least one point that's not in both regions, or in one or the other region. So the interior of a closed plane figure is defined to be the connected region bounded by the curve that's contained in the interior of a circle. So here we see that there's some circle here that's going to completely contain this connected piece, and so that is the interior. But there is no circle that's big enough to contain all the rest of it, which would be the exterior. And if it's a simple closed plane polygonal curve, then that's a polygon. So it takes a little bit more work to do this, but notice we've established some nice little hierarchy, that we've got some curves, continuous curves, with under that we've got polygonal curves, plane curves, closed curves. Putting some of these things together, we eventually get our way down to polygons. Okay, we have some theorems about closed plane figures here. Closed plane figure partitions the plane into 3 disjoint sets: the closed plane figure itself, the interior of the closed plane figure, and the exterior of the closed plane figure. Circles, triangles, and quadrilaterals are closed plane figures, and a line segment is a simple non-closed curve. And then with these definitions here, and the definitions that I gave before that didn't deal with curves of triangles and quadrilaterals, then we can prove proposition 67 that triangles and quadrilaterals are actually polygons. Now, if you were to actually, so you can actually talk about triangles and quadrilaterals without talking about any of this stuff about curves and continuity and all that. But if you want to talk about this, either informally or formally, and set that up for curves, then you could just define a triangle as a three-sided polygon and a quadrilateral as a four-sided polygon if you want to do that stuff first. We're going to take the approach that I have here, but we could do that. Some general properties of polygons. The minimum number of sides of a polygon is 3. The number of sides of a polygon equals the number of vertices of the polygon. If a polygon has n sides, then it has n minus 3 diagonals from each vertex for a total of n times n minus 3 over 2 diagonals. We can name a polygon with n sides. We could call that an n-gon. And we have some special names if we have a small number of sides. So 3 sides is called a triangle or a trigon. 4 sides is called a tetragon or normally a quadrilateral. 5 sides is a pentagon. 6 sides a hexagon. 7 sides a heptagon. 8 sides octagon. 9 sides nonagon. 11 sides undecagon. Yeah, that's right. That's out of order. 10 sides is a decagon, then 11 sides undecagon, and 12 sides dodecagon. And so for polygons with more than 12 sides, we'll typically not use special names in this class. So for example, a 15-sided polygon, we'll just call it a 15-gon. And if it's a variable sides, well, we don't know, we'll just call it an n-gon. But there are conventions for naming more polygons with more sides. This website right here is a site that allows me that shows examples of a naming convention that goes all the way up through 999 sides, and so it's a place I just Googled this, and this is one of the first hits I got. And this shows you how to go up to 999 sides. And so there are ways to do that. We typically won't be worried about this too much in this class. We're going to mainly just worry up for these up to 12, and then we'll just worry about that. And then here's some definitions, some more definitions for polygons in general. Okay, so there's some basic definitions there for polygons.